In the previous video, we understood what are the characteristics of a standing wave, correct? Now, in this one, we'll understand what is the frequency or time period or wavelength, whatever it is, that for a particular standing wave. Okay, generally we talk about the frequency and the wavelength. Let's try to understand. Now here, in this derivation, first thing what you need to understand is that whenever we talk about a string, okay, be very careful about understanding, we are talking about a string. Alright. Now you have two ends are fixed for a string, correct? Now this one end and one end, and when you struck the string, you will have the wavelength. You basically have a standing wave. So let's say that the 2 points, the two fixed points, say those two are x is equal to 0 and x is equal to L. Alright. The next thing what we have, the wave is set up between these 2 points. This is where we are going to understand how superposition of the waves is going to occur. Alright, let's do the math now. Let's do the analytical treatment of finding the wavelength in a standing wave. Fair enough? Okay, so in this case, what's going to happen? Let's say, see, one wave is going to move from left to right and one more is going to move from right to left. That's where you are going to have a standing wave, correct? Say the one which is moving from left to right, it's moving in the positive x-axis or positive x direction. So we can say that y of x comma t, or you can say y1 of x comma t, the first wave, this is equal to r sine of omega t minus kx. First wave. The second wave comes in the opposite direction. So you can say that y2 of x comma t is r sine of omega t minus kx plus pi, 180 degree phase shift. But what is sine of pi plus theta? Minus sine theta. So this becomes minus r sine of omega t minus kx. Okay, one more thing. The second wave, it is coming from right to left, which basically is moving in the negative x direction, correct? So another change in the second wave is that if you look at this minus x minus kx part, the value of x is minus x, correct? Because it's coming from right to left. So how the second wave is going to change now? So the final equation would become y2 of x comma t is minus r into sine of omega t plus kx. Okay, that minus kx becomes minus k into minus x. It will become plus kx. Alright, now we have two waves, y1 and y2. Now superposition. Superposition is what? We have to add both of them, correct? So if we are doing, so we can say by principle of superposition, we have y is equal to y1 plus y2, isn't it? So we have y is equal to y1, which is given by r sine of omega t minus kx. Next y2 becomes minus r into sine of omega t plus kx. This is what we have. Now we take minus r common. That means here y is equal to minus r into sine of omega t plus kx minus sine of omega t minus kx. This is what you have. In the next part you have to take, see, it's subtraction of two sine functions. It's like sine c minus sine d, correct? So when you have sine c minus sine d, again we have to apply the same logic, that is, we have to apply the transformation formula. Let's apply that and let's see how it's going to go. Transformation formula is what? When you have sine c minus sine d, you have 2 cos c plus d by 2 into sine c minus d by 2. Make sense? Now in this one, the very first thing what you are going to have when you apply these two formulas, then you will get the formula that is y of x comma t is equal to minus of 2r sin kx into cos omega t. This becomes the net displacement of the particle in a standing wave. Let's be very, very clear, in a standing wave. Now that you have a standing wave, let's try to understand what is the value of that y for different positions. In the sense, see, there are two fixed points, correct? One is that point x is equal to 0 and another one is x is equal to L, correct? So in the first case, that is what we'll do. So let's take this formula. We'll keep this formula. With this formula, we'll try to take different cases. So in the first case, that is when you have x is equal to 0. See, what do you have? If x is 0, then the y value is going to become 0. Because look at the argument, look at this amplitude, 2r sin kx. When x is 0, sin 0 is 0. So the total displacement will be 0. That means when x is equal to 0, we have y is equal to 0. This basically is a node. Remember nodes and antinodes? This is the first one. In the second case, suppose if you take x is equal to L, then y is equal to, what do we get? Minus 2r cos omega t into sin kl, because in place of x, we have L, correct? So what do we do after this? Now, even at the other end also, end is a fixed point, right? Since end is a fixed point, now what do you get? It's also going to be the node itself. That means, even when x is equal to L, y value has to be 0. Or in other words, minus 2r cos omega t into sin kl is equal to 0. Now, sin kl has to be 0. Or in other words, we can say that instead of 0, we can write this as sin n pi. That means sin kl is equal to sin n pi, where n basically belongs to set of whole numbers. Alright, 0, 1, 2, 3, 4, whatever. Okay, now that you have kl is equal to n pi, now what do we have? You're going to have kl is equal to n pi, or what is k value? 2 pi by lambda, or 2 pi by lambda into L is equal to n pi, or lambda is equal to, see, pi and pi cancels, isn't it? So lambda is equal to 2L divided by n. So whatever the value of lambda we are going to get here, this is going to represent the first, second, third vibration of the string. Okay, we are talking about vibration of the string. Now let's do for different lengths, what is going to be the value of lambda? Okay, lambda frequency will all figure out this one. Suppose let's say you have, see, this is one end of the string. Say this is another end of the string. Now between these two, see, you are going to have one like this and you are going to have another like this. So basically this is x is equal to 0, x is equal to L. Now this entire thing, whatever we have, this, the midpoint is going to be the antinode, maximum displacement antinode. And the other two, this is a node, this is a node, isn't it? See, in this case, what do we have? Lambda value is what? Lambda is equal to 2L divided by n, isn't it? And in this case, what are you going to have? You're going to have lambda 1 is equal to, so lambda 1 is equal to 2L divided by 1. Because what do you have here? You're going to have just one wave, isn't it? Or this is the first harmonic whatever we are discussing. Alright. So 2L by 1, or you have L is equal to lambda 1 by 2. See, the total length is half of the wavelength of the wave. Okay. Now this value, whatever we have, no, lambda 1 is equal to 12. Suppose if you need the velocity or if you need the frequency, then what do we do in this case? See, we know that velocity v is equal to f into lambda, isn't it? So in this case, what you will have? You will have v is equal to f1 into lambda 1, or you have we have f1 is equal to v divided by lambda 1, or v divided by 12. Since you have v by 12, then you will have f1 is equal to 1 by 12 into root of t divided by m. See this frequency? This frequency has a special name. The special name given to this frequency, we call this as the first harmonic, or this is also called as the fundamental frequency. Fundamental frequency. Okay, this plays a very important part in any string instrument, the fundamental frequency. Whenever they set up the string in any guitar or veena or sitar or whatever, any string instrument, this fundamental frequency is extremely important. Okay, likewise we have different ones. Okay, let's do the same thing for second and third harmonic now. For the second harmonic, so what we'll have is, so we'll have 1, 2, 3 points. So first goes like this. This is going to be 1. This is going to be the second one. In the sense, there is a node, node and node. So there are 3 nodes and there are 2 antinodes here and here. This is how it's going to be. So in this case, what we do, a lambda 2 is equal to 2L divided by 2, which is basically L. That means 1 full wavelength. Alright. So since we have 1 full wavelength, then you will have F2 is equal to, see, you will have F2 V divided by lambda 2, or you will have this as V divided by L. Multiply and divide by 2. That means you will have this as 2 times V by 2L. But V by 2L is F1. That means F2 becomes 2 times of F1. This is called as the second harmonic. Second harmonic or first overtone. Same way, the third harmonic is going to be 3 times of F1, correct? And the third frequency or the third harmonic is the second overtone. Likewise, for each and every string where 2 ends are, they're plucked together, you can calculate what is the fundamental frequency. From there, you can calculate each individual frequency and the next overtone, whatever we are going to get. In general, what we have is that, suppose say you are calculating the nth frequency. Okay, then you will have Fn is equal to n into F1. This becomes the general formula. This becomes the nth harmonic and n minus 1th overtone. This is what we are going to do in strings.